Okay, I think we can start. Welcome everybody to this new webinar by IABSE. IABSE is the International Association for Bridge and Structural Engineering. I'm Fabrizio Palmisano. I'm the director of the engineering consulting company called PPV Consulting based in Italy, in Bari, south of Italy. And I'm here to introduce this webinar as vice chair of the Italian group of IABSE. The topic of this webinar is great engineers, and we will talk about Riccardo Morandi. This is the first of a new series of webinars organized by the Italian group of IABSE focusing on great engineers. The format of this webinar is the so-called duo. So we will have a couple of presentations. The first presentation would be relevant to the works of a great engineer, Riccardo Morandi today. And the second presentation will be relevant to a topic strictly connected to the great engineers. And today we have the pleasure to host Dr. Nicola Scattareggia, who will talk about his PhD thesis, who has won the IABSE award on of the best PhD thesis in 2024. We have the honor to host Professor Enzo Siviero, who will talk about the works and life and of Riccardo Morandi. I will give you a short introduction of IABSE, and then I will leave the screen to the moderators, Dr. Filippo Landi and Dr. Enrica Lenticchia from the IABSE Italian group. The IABSE mission is to exchange knowledge and advance the practice of structural engineering worldwide. It covers all aspects in structural engineering, all types of structures and structural materials, or all aspects of the construction process. It was founded about 100 years ago. It collects more than 100 countries, more than 60 national groups, and about 1,900 members. The objectives are to promote cooperation and understanding among all these concerned with structural engineering and related fields by worldwide exchange of knowledge and experience, to encourage awareness and responsibility of structural engineers towards societal needs, to encourage actions necessary for progress in structural engineering, and to improve and foster cooperation between organizations having similar objects. This is a global association which have a local presence in national groups. And as I said before, we have more than 60 countries all over the world. This webinar has been organized by the Italian national group of IABSE, the so-called IABSE IT. It was refounded almost 3 years ago, and its main activities are to coordinate new technical Italian task groups to discuss on specific topics, to disseminate activities of the task group in the journal of IABSE, in the bulletins, workshops, special sessions at IABSE conferences, and to have training activities such as this webinar, conferences. We've had our first conference in last October, and technical visits. The heart of the IABSE, the International Association, is the so-called Technical Committee, who is responsible for the overall technical activity of the IABSE and coordinate the committees relevant to the outstanding structure and paper awards, the commissions, the SEI editorial board. SEI Structural Engineering International is the journal, the official journal of the IABSE, the bulletin editorial board, the Young Engineers Committee, and finally the new founded IABSE Academy. IABSE activities, the Commission. The commissions are long-term bodies which encompass a broad range of topics covering the life cycle of a structure. For the time being, we have 6 commissions on performance and requirements, conceptual design, structural analysis and evaluation, construction methods and processes, existing structures, and sustainability. They coordinate many task groups. Task groups are short-term units targeted for well-defined objectives, typical investigation of technical interest or concern. There is no need to be a member of the IAPSE to join a task group. So I'll invite all of you, also people who are not members of this association, to join our task group to meet experts all over the world in a specific field. IAPSE organize each year some conferences. These are the forthcoming conferences. We will have in May the IAPSE Symposium in Tokyo. The topic will be environmentally friendly technologies and structures. And we have the Congress, the official IAPSE Congress in Ghent, Belgium in August this year. The topic will be the essence of structural engineering for society. IAPSE has three kinds of main publication. We have surely conference proceedings, but we have also the official journal on structural engineering called Structural Engineering International, where we can find not only technical papers, but also valuable scientific papers. We have IAPSE bulletins, we have guidelines, case studies, and structural engineering documents. Structural engineering documents are special reports of high scientific and technical standard, focusing on the advancement in structural engineering. On the IAPSE website, you can find also the IAPSE learning platform. For the time being, it is divided into 5 parts, one relevant to webinars like this, keynotes, lectures and courses, reports, and toolbox. IAPSE is reorganizing the entire platform and adding some special courses that will be delivered, I hope, in this year. One important activity of IAPSE is to disseminate the knowledge of structural engineering. Is the Young Engineers Program. The scope of the Young Engineers Program is to liaise young engineers with conference organizers, advocating for IAPSE through social media, and facilitating opportunities to bridge budding engineers with the experts among the IAPSE fellows. We have also the IAPSE awards. We have many kind of IAPSE awards. One group is relevant to people and paper awards, and the other to projects and technology awards. And the deadline for nomination is the 31st March 2025 for the 2025 awards. With this, I would like only to remind you that the webinar will be recorded, and it will be also available on the IAPSE platform, e-learning platform, and on the YouTube channel. And if you have questions, you have to put the questions in the Q&A section of Zoom. Please remember, in the Q&A section, only in the Q&A section of Zoom. And there will be, at the end of both presentations, there will be a final discussion and Q&A part. So with this, I've completed my general introduction, and I give the screen to Erika Lenticchia and Filippo Landi for the introduction of the speaker. Enjoy the webinar.
Thank you, Fabrizio, and good afternoon, and welcome also from my side. I am Filippo Landi. I work at the University of Pisa. And as was mentioned before, we have today 2 speakers, Professor Enzo Siviero and Dr. Nicola Scattarreggia, to talk about Riccardo Morandi, his work, and research linked to his activity. I remember that the webinar is recorded and will be made available on the IAPSE website. As mentioned before, you can put your question in the question and answer section that you can find on Zoom on the bottom. And we will start with the presentation of Professor Siviero. Professor Siviero is the rector of eCampus University in Italy. He has previously served as full professor of bridge design at the University of Venice. He is consultant professor at Tongji University in China, and is a very well-known bridge designer. His traveling exhibition, Bridging, is internationally celebrated for its excellent synthesis of educational research and professional practice. He organized several workshops and conferences on bridge engineering, like the IABSI Symposium in Venice 15 years ago. He currently holds the position of Vice President of the Structural Engineers World Congress, and his remarkable contribution to bridge engineering has been acknowledged with several prestigious awards, including the Medal of Excellence of Engineering Education from the World Federation of Engineering Organization. So please, Professor Siverio, the floor is yours. Please share.
Thank you very much for this invitation. I'm very happy because I was member of IAPSE since I think 50 years ago when Professor Turleman was president, and my mentor Giorgio Macchi was vice president. We organized just 15 years ago in Venice this fantastic symposium. By the way, I would like to explain you who is Riccardo Morandi, although the time is not so much, but I will try to go ahead. Yes, you can go for the first slide. Riccardo Morandi is one of the most important bridge designer all over the world. There is no, but nobody knows, or few people knows that Riccardo Morandi was also urban planner, and this is in Colleferro. We call it the Morandian city. I'm sorry because I had no time to translate it into English, but I would like to show with a few slides what Riccardo Morandi made in the field of buildings and urban planning. He was a kind of architect at that period. He worked between the two wars. Please go. This is just to a cinema, a theater for Bombrini Parodi Delfino. It was a very important company. And for this company, he organized a kind of workshop people for let them live in connection with the factory. He was also making some work during the war, and this is another problem. Please. I would like to show some of the building he was making just right after the war. I don't enter too much, but during the war he was working so much. Next time, next please. And this is just to show how delicate is his design. Is a kind of engineer architect as it was many years ago, say 1 century ago. After Nervi, I think Morandi is the most important one in Italy, together with some other, but of course. Next, please. Città Morandiana is now in the tentative list of World Heritage. So it is to be recognized the importance for the social situation of the building. But the most important one is just bridges. And I show you some of the bridges he made in his life, please. This is Riccardo Morandi. He was sketching by hand, you know. This is also very important. When you design by hand, it means that your brain goes directly to the sketch. This is one of the sketches, please. Another one is Riccardo Morandi. He was very old with a bridge in Rome. But you see on the right-hand side, you have this Byzantis Fiumarella bridge in Catanzaro, which is also part of this seminar. Please. This is the first. Okay, let's come back. Yes, this is the first bridge he made in South Africa. South Africa, and you see that the arch has something very peculiar because the standing are not vertical but somehow inclined. This gives you an additional safety situation, but at the same time an architecture feature which is very nice. Next, please. You see here how he was building the bridges, because the concrete bridges, that arch bridges, that time was with the scaffolding, very important. But in that case, he prefabricated the semi-arch and then he inclined it, as you see here. I have no time to discuss, but of course, all these things without the instrument we have now and the possibility we have with the computer was a very difficult task because everything almost was made by hand. You see, it is almost 60 years ago. Another bridge is this one, which is a footbridge. And again, he worked with the semi-arch, moving from one side to the other. And the form, it is a parabola, of course. You see on the right-hand side, the bridge as it is finished, but next. What is interesting is that it is an artificial, no, just one moment. If you come back one moment, I would like to show you that even when the water is there, you see the impression of the bridge is somehow very natural. And this is one of the most important features of the design by Morandi. Next, you have here the Fiumarella or Byzantis. Fiumarella is just the river which is underneath, and Byzantis is the person who just promoted this bridge. There are a lot of features that we can discuss. One for us, you see the X elements which are able to reduce the slenderness, and it is also something which is from architectural point of view very important. At the same time, the structure. So the combination of engineering and architecture, I always say a bridge between engineering and architecture. Yes, myself I'm dealing with since 40, 50 years. Next, please. Other views. I visit this bridge a lot of time. I would say that Catanzaro town is more important for this bridge than for other features. Just to mention how the arch is attached to the abutment. You see, you have a bifurcation of the elements and this is showing also the bending moment organization, which is tension and compression. And this is for my student. I was teaching bridges to the architects, so I had to talk with same language of them. Please, we can go through other too much, but anyway, the other one was just showing that even lighting, the lighting system is giving the impression of the bridge. We are talking about a bridge that this is more than 200 meters span, of course. Next, please. Next slide, you see the scaffolding, which is also a work of art. I mean, it's very important, a piece of art. Even the scaffolding, sometimes it's more important the execution, during the execution, because nobody can organize in very easy way the behavior of the bridge. Next, please. Here you see details of the scaffolding, which is, to my opinion, like a picture. It's fantastic. I like it very much because the site work is, to my opinion, a very important feature. Every structural engineer should know how it works, how to erect the things, how is the behavior during construction. Next, please. This is maybe one of the most important bridges that Riccardo Morandi made. At that time, we are talking about around 60 years ago. The Italian contractors were working all around the world, and Morandi was working for the contractors. This system is a peculiar situation of Morandi. Please. Laguna, Maracaibo Lagoon. And in that case, you have the cable state, which is steel. In other cases, we see he used steel, but embedded in concrete. This is a peculiar situation which gives some problem, of course, but at the time it was very, very cheap. Next, please. And we come to Polcevera Bridge, which is well known not only because Genova, they say they call this their Brooklyn Bridge, although there is nothing to do with Brooklyn, of course, but it has been demolished a few years ago after the collapse of that part. And I say that time that it was a murder of a bridge because there was no reason, no real reason to demolish it. Please, next, please. This is another bridge which is in Libya, in Cyrenaica, well, in Kufa, which I know it very well because I visited many years ago. And it is the same system, but a little bit more span. It is 250. Next, please. Next. A picture which is with the color, because it is done the sun is just illuminating it, and the result is this one. It's a kind of monument in the landscape. Next, please. This is in Colombia. This is Barranquilla bridge. To my opinion, is better than the other one because the stands are inclined, and the detail of the pylon is also more interesting than the other. It's smaller size, but it gives you details. We have now some details of the construction. Please, next. Time is running again. You see the system, it is the cable in steel, then embedded in prefabricated elements in concrete, and then pre-stressed. This gives some problem for the injection of the mortar and so on. Please, next. Now we come to Polcevera. How was this murder, I say? Please. This is the illustration in the newspaper when in 67, inaugurated with the president of our republic at that time was Saragat. Next, please. Some detail, which is very peculiar because there is not only the main span, more than 200 meter span, but also this additional span, which is 70 meter approach with this V shape, which is unfortunately, it was very interesting. The whole bridge is was more than 1 kilometer, half with this system, so-called Morandi system, and half with this V shape, with the element prefabricated, part prefabricated, part cast in situ. Next, please. Scaffolding is very interesting because there was at the initial part was only cantilever and not the ties element. Next, please. I don't comment so much. I think we can go and leave a few seconds because time is running. This is thus details of the site work. Next, please. Also problem with the concrete. This is the final design before. Next, please. Crollo, the collapse. It's now almost 7 years, and it was really one of the most worst situation for the structural engineering. This is how it happens, how after the collapse, so-called Mylon 9 collapse, and the reason is not very, very clear now, although we have some ideas, probably because of the injection of the mortar was not enough, some corrosion problem and so on. But when it collapsed, the bridge was no traffic, which is also very strange. Maybe there was also a fatigue problem. Next, please. We propose ourselves to close the part which has been collapsed. Next, please. I imagine this, you see, this Michelangelo, the creation in you have the two fingers that are connecting, and this finger that accept to have another connection, please. This is our idea, though the V shape, we change in other V shape to connect on the other side with the reverse V shape. Our proposal was to have around 200 meters, a little bit more, and span, and it is We used, of course, steel because it was not possible to replace the situation now 50 years ago. Next, please. I tried to condense. You see, it was for us something to show the transition from one part to the other, because my attitude personally and the teaching to my students is mainly to devote an important part to the venustas, it means the beauty of the bridges, the architectural feature, design, landscape, and so on, not only the structural engineering. I know that in IAPS there is also quite attention to conceptual design, and the conceptual design should not only a design of structural, it should be also a design holistic, all together. Next, please, just to show you a rendering. That was not accepted, of course, because they decided to demolish the bridge because they considered the bridge the responsible of the murder of the, unfortunately, more than 50 people. And it was really a tragedy. But there was no technical reason to demolish, it's only political and social reason. Next, please. These are a rendering, of course, just to show that we can combine one part to the other. So it would be considered at least in a kind of comparison. But the political decision was to demolish the bridge. Therefore, we made this effort just for history, for glory or not glory, I don't know. Anyway, you can judge. And I think the most appropriate place to discuss this is IAPSE. This is my point of view. Next, please. This is also very interesting because you open the arms, it seems that you are praying to the God that nobody can repeat this. And next, please. This I work with my co-worker. This is what they find finally. They demolished the bridge. And the inauguration of demolition by the politician was something that for me was a kind of bad impression. Any demolition is a kind of losing our life, our heart. Next, please. And this is the proposal of Renzo Piano, the original one. And I think he proposed three span of 100 meters and the other span 50 meters. We remember that the span by Riccardo Morandi was more than 275. The reason why they reduced the span is not very, very clear, but you know, it was Renzo Piano is one of the most important archistar, we call it, all over the world, and surely the maximum expression of the architecture in Italy. But as far as the bridges is concerned, I don't think that Renzo Piano gave his best idea, unfortunately. But this was the solution. Demolish the bridge, the existing part of the bridge. It means that they demolish something like 900 meters of bridges and replace with this one. To my opinion, there was also another mistake to demolish because they could have the possibility to investigate the bridge in the size one by one. The existing bridge, if they decide to demolish, before demolishing, they can work with experimental test, invasive, not invasive, destructive, non-destructive, because if you have to demolish afterward, then you are free to do whatever you want. They decide to demolish before any additional investigation. Now we are in the court, and I don't think they will get the final result within next years, because of course all the most important bridge in structural engineering in Italy, they are on one side or the other side. They're fighting for the conceptual decision, how is the real reason of the of the collapse. Next, please. Just to remember that an Italian company, the Delma, which is Maltauro system, they made a replacement and the rehabilitation of the Wadi Kuf bridge. And this is what they've done. And this could be done also for Genova. It means that they decide to demolish, although there was a possibility to revise completely, getting also the seismic the seismic functionality, because in Italy since 20-30 years we have the seismic situation over Italy. You see also the loading test, which is in Italy absolutely compulsory. Next, please. Now I show you the bridge, so-called Ponte San Giorgio, the San Giorgio Bridge. San Giorgio is the patron of Genova by Renzo Piano. We can go, just you can judge what is the bridge, which is not bad, of course, but it seems to me a little bit old in the conceptual design. And not very cheap, because the cost of this bridge is per square meter is the equivalent to the Millau Bridge in France. But you can imagine what is the difference from the two. But we come back to the no, it's okay. We show you that in the past we had a similar situation. Next. This is a bridge designed by Luigi Negrelli. Luigi Negrelli was born not far from Padua, is in Veneto, and he was also a good, fantastic engineer. He was the first having the idea for the Suez Canal. Then the French arrived and they make, but this was his bridge in Desentano, which is near Garda Sea, in 850. During the next, please. During the war, this is what happened. The bomb was destroying just two spans, and instead of repairing and getting the continuity, maintaining the quality of this design. Next. This is what they made. I don't like to comment it, but of course, it seems to me that after the Second War, we have lost the capacity of designing nice bridges, bridges that are impressive, not only because the engineering feature, but also for landscape and architectural feature, which is very, very important. If you compare this bridge with the other one, there is a kind of gorge. It seems that we've lost the paradise. We go to the down, but this is my impression, of course. Next, please. Okay. Then I'm sorry that I had to run so much like in the Olympic game marathon, but I try to speak not only with my brain, but also with my heart. And this picture remains as a disaster, psychological disaster. You have lost a nice bridge, and you have a common bridge. The only advantage of this new bridge that has been designed by Renzo Piano. Okay, thank you so much. Any question, I will try to answer, of course. And thank you for helping me, because I'm not so good in getting this mechanism, because I'm so old. Thank you so much.
Thank you very much, Professor Siviero. I think that the question can be done, and remember that the question can be done by using the Q&A at the bottom of the Zoom meeting, and we will do a discussion all together at the end of both presentations. So thank you again, Professor, with your prescient insights about the figure of Riccardo Morandi and your wise words and considerations. And now I would like to introduce the next speaker of this webinar, who is Dr. Nicola Scattareggia, who is a postdoctoral researcher in structural engineering at the University School for Advanced Studies of Pavia. He was a visiting researcher at the University of Berkeley in the United States, and the main research activity of Dr. Scattareggia is in the field of modeling, analysis, and design, as well as strengthening of bridges. And his work received international recognition and prestigious awards. And in particular, in 2024, he won the IEBC Best Doctoral Thesis Award for his PhD thesis titled Structural Assessment of Reinforced Concrete Bridges Up to Collapse. And I'd like to remember that regarding this award, I'd like to remind you that the deadline for the application of the next Best PhD Thesis Award of the IEBC is about to end at the end of March, the 31st of March. And now I want to go back to Nicola, that he will now present his contribution about structural assessment of up to collapse of RC bridges. And if you have any question, we will do it after the presentation. So I will leave the screen to Dr. Scattareggia, please.
Hello, everyone, and thank you for the presentation. Can you hear me?
Yes, loud and clear.
Okay. So again, hello everyone, and thank you for the introduction and the presentation of my profile. Before starting the presentation, I'd like to thank the IABSE Italian group for the invitation. And as already introduced by Dr. Lenticchia, this presentation is about the work that I carried out during my PhD, which thesis has been defended on 2023. And as you can see also from the presentation title, this presentation is about the structural assessment up to collapse of RC bridges. If we look at our modern infrastructures, we can see essentially that the backbone of our infrastructures date back to the Second World War, and this was a consequence of the economic boom that we had during the 60s. This happened both in the United States, thanks first to the action by President Eisenhower first and later President Kennedy, but a similar thing can be also observed in most of European countries, among which my country, Italy. And as a result of the construction of these bridges during the 60s, nowadays these bridges, many of these bridges are more than 50 years old. If we focus in Italy, we can have beautiful examples of bridges that have been constructed during such period, as you can see in this slide, and also as shown before by Professor Siviero, specifically referred to the work by Professor the engineer Riccardo Morandi. But over the 6,000 bridges that more or less we can count in Italy, we can say that about the 50% of this bridge is more than 50 years old. And as a result of their natural aging in combination with an uniform management strategy and effect also of climate change, as highlighted by also the collapse of the Morandi Bridge that has been presented before, we observed many bridge collapses that prompt the need to have changes and to pose attention to the safety of existing bridges. Indeed, this has been also highlighted by recent guidelines that have been issued in 2021. So it was 2 months later, after the failure of the Morandi Bridge, that I started my PhD. And it was at that time that I decided to dedicate my doctoral studies to analyze and understand from the bridge failures. But at that time, there was a major question that was why and how we can do failure assessment. Of course, we have some needs when we think about existing bridges. And among these, we have the importance of identifying hidden deficiencies and how these deficiencies and defects can have an impact on the residual capacity of existing bridges, explicitly considering their robustness. Another necessity was to try to assess the resilience and resistance of these bridges when subjected to exceptional or undesigned and extreme loading scenarios, as well as the influence of deterioration, and then also because the analysis of collapsed structures may help to prevent future failure. When we deal with the collapse assessment, essentially, usually we rely on the structural analysis. We usually rely on the use of finite element modeling. But as you probably know, finite element modeling belongs to the family of continuum-based techniques. So they pose some limitations when dealing with the collapse assessment of structures, where we can expect to have separations within the structures and also collision. So in this case, the most useful tool, numerical method that we can use to deal with this kind of problem are the methods that are based on the discrete element that made use of discrete element models. On the other hand, I want to say that traditional discrete element models pose some limitations due to the time that they need to run the analysis, considering that most of them are based on explicit on the solution based on the explicit method. So it was for this reason that at the time I selected the applied element method as a method able to reproduce the structure response from the very initial elastic stage until to the simulation of the complete collapse of the structures. But what is the applied element method? For those of you who don't know this method, essentially this is a method that has been, it's relatively new because it has been proposed back to the 2000, and specifically within the applied element method, if we think to reinforced concrete structures, we can see that a component is essentially schematized as an assembly of rigid units that are connected one each other by zero-length interface springs that account for both the axial and the shear response of material. And considering that previous application proved that the applied element method was capable of reproducing in a good manner the behavior of reinforced concrete structures, mainly building actually at that time, in a reasonable computational time frame, this pushed me for the application of this method to the analysis of to the collapse analysis of existing reinforced concrete bridges to try to learn from the past failures. One of the case studies that has been considered has been exactly the Morandi Bridge that has been already illustrated by Professor Siviero. And the Morandi Bridge collapsed at the age of 51 years old, so well aligned with the age of most of our operating bridges in Italy. I will skip actually now the presentation, the description of this bridge, because already Professor Siviero described it. But I want to say that this masterful piece by Riccardo Morandi represented a key infrastructure for the Italian road network, and we know that it has been designed in the early 60s. So I want just to say that this structure, it has been masterfully designed by Riccardo Morandi, but according to the knowledge of those times. So we can say that there have been elastic calculations and a few considerations on redistribution of the forces, time-dependent effects, fatigue, and corrosion. You can see here in the red circle the portion that collapsed due to the failure of one of its stay that is indicated in this figure on the right side. Here you can see also the full schematic of the bridge, and it was again the balance system number 9 that is highlighted in the slide in red that collapsed on the 14th of August 2018. I do not discuss the details. Here you can see the distribution of debris, the peculiar distribution of debris in the aftermath of the collapse. Now we don't have time to discuss the exact position and residual displacement and rotation of each part of the bridge, but this was quite interesting at that time to be analyzed. On this bridge, actually, I spent a lot of time. I would have a long story to tell you about the studies that I carried out since the aftermath of the collapse, because initially we have done some preliminary studies where we understood before the publication of the video of recording the collapse that the cause was associated with the failure of the stay. Later, in addition to the material that was publicly available, I had also access to the classified material and the video recording the collapse and all the as-built information about the structural details, materials, and so on that have permitted to build numerical models faithfully to the reality. For this case study, I want just to highlight the importance of the modification of structural details. And what was interesting was that a minor modification in the cable layout along the deck of the bridge would have caused just a minor influence on the torsional capacity itself of the bridge itself, but this would have caused the migration of the critical failure of the critical section, as you can see in this finite element modeling of a portion of the bridge. So there was a switch of the critical section. So at that point, the question was, does this migration also impact the global bridge collapse mechanisms? Because we are thinking about the collapse assessment of these bridges. And based on all the information that were available at that time, so both the as-built structural details and as-built materials, I had the chance also to build an applied element-based numerical model that you can see in this slide, where have been reproduced all details. This is a model that counts about 600,000 degrees of freedom. And actually, the analysis showed that a relevant impact of as-built details on the collapse mechanism of the deck, but as predicted by the finite element modeling that I shown in the previous slide. But most importantly was the huge impact of this migration of the critical failure on the collapse mechanism of the entire bridge, as you can see comparing the frames in the top part of the slide with the ones on the bottom part. And however, as you can see also from the comparison that is shown in this slide between the numerical and observed collapse, this comparison clearly demonstrates that there were no doubts that the failure of the bridge was caused by the stay failure, the one that I've shown you pointed before in the introductory slide of this bridge. But at that point, I was trying to go more in depth, try to understand why the stay failed. And among all the other possible loading scenarios that I have explored, In this presentation, I would like just to talk about two of them. And specifically, what we know, what we clearly knew was that at the time of the collapse, there was a windstorm, and also an heavy truck was passing on the bridge and was transporting an heavy steel coil. But in addition to that, the autopsy, I would say, of the failed stay also showed that in the top part of the stay, where the stay failed, there were hidden construction defects. Indeed, as you can see from the figure, the cable layout was not the one that was designed by Riccardo Morandi. There were the presence of voids, the cables layout, the cables were congested, and so on. And in addition to these construction errors, also high levels of corrosion at that section have been detected. So now I will go, I'll try to speed up a bit, but essentially in this slide, you can see that the geometry layout would have a relevant impact on the axial force bending moment capacity of the stay. Indeed, the green one, that is the one corresponding to the as-built details, it is rotated towards the north with respect to the blue one, that is the capacity domain associated with according to the as design details. In this slide, you can instead see the huge impact, the significant reduction of the capacity due to the deterioration of the cables mainly associated with the corrosion. You can see that there are two reduced capacity domains, essentially because they were based on two different ways to assess the residual area of the cables that were composing the stays. And then later, the capacity between the two possible estimates that here I'm showing you, the most likely capacity has been identified through a back analysis approach, thus considering the loads that were experienced, supported by the bridge a few weeks before the collapse. So in this way, the study turned out that essentially the green curve was representing the best estimate of the residual capacity if we compare these two possible estimates with the permanent loads that were acting on the bridge on the day actually of the collapse, plus the typical wind velocity, wind action that usually was recorded in such area. In addition to the fact so that we had a residual, a reduced capacity, I also explored the potential of a steel coil impact on the steel deck. Indeed, this was one of the different hypotheses that have been formulated. I want to say that about this potential triggering factor, there are no evidence that this kind of event happened, but I want just to say that this kind of incidents can occur, as you can see in the bottom part of this slide. This was important to be studied because according to initial estimates that have been carried out by Professor Calvi, the increment of force produced by such impact was sufficient to produce a demand exceeding the residual capacity of the stay as estimated, as I have shown before. Based on this, by using advanced applied element models, I investigated the potential force generated by an impact of this type, studying different sources of uncertainties associated with the track velocity, position, and etc., etc. And later, fewer analysis have been run also other analysis using the global bridge model and by simulating the failure of the falling of the steel coil and the impact in a specific position along the bridge. And what is important to say of this slide is essential that this kind of modeling permit us to reproduce the complete collapse sequence of this kind of bridge, permitting us also to compare the debris distribution that in the specific case shown a compatible position of the debris between the numerical and observed one, also in terms of position of the steel coil. Other studies have been also performed to show if also strong thermal gradients would have the potential to trigger, to introduce an action capable of exceeding the capacity. And as you can see in this figure, essentially the yellow bandwidth that represent the possible excursion of the demand due to the thermal gradients would have also matched the residual capacity of the stay, as you can see in this figure. So now I want to very fastly pass through another case study that has been studied. I don't know how much time still I have. I think a couple of minutes. But it was 2 years later that there was a collapse of another very important bridge, that is the Capriola Bridge, a multi-span bridge. Also, this bridge has a beautiful story. I want to say just that this bridge has been first built at the beginning of last century, and it has been then bombarded by Germans during the Second World War, and it has been rebuilt in the 40s. It is just important to say that during the reconstruction, there was a major change from a fixed arch solution to a 3-inch solution, and this was done to preserve the original piers that have been bombarded with the original bridge, and this was done to make possible the accommodation of rotation and adjustment of the piers that were bombarded. Here you can see the schematic of the bridge. It was a 5-span bridge, and in the bottom slide, part of the slide, you can see some of the details. I want just to say that it was a 3-inch arc bridge. And this bridge in the 90s undergone under major changes with the addition also of a slab to enlarge the carriage. Similarly, as the Morandi Bridge, also in this case, I built an applied element-based model with the aim to understand, to simulate different loading scenario and to understand the response of this bridge until to the collapse. In this case, I have done many validation of the model, as actually I have done for the Morandi Bridge, but I didn't have the chance due to the time constraint to show in this presentation. But with this model, I took into account different sources of hazard associated with the natural factors, so hydraulic factors at piers, erosion, scour, the presence of a slope slippage on one side of the bridge, material deterioration, the damage accumulation due to the overloading, specifically with the particular reference to the deck enlargement in the 90s, the presence of past earthquakes, but also the effect of construction errors with the variation of the dimension of the concrete hinges. I have implemented many models and framework to investigate the previously mentioned scenarios, but I want to summarize that there were no major problems associated with the overloading, damage accumulation, and material deterioration. But on the other hand, the bridge was sensitive to the pier and abutment rotation and displacement, as well as to the physical dimension of the concrete hinges. And as a result, the presence of the slope slippage that was present on the Capriola side of the bridge, the overloading coming from the addition of the slab to enlarge the carriage, in combination with a reduced rotational capacity at the concrete hinges due to an increase of a reduction of the throat of the concrete hinges, it could have been possible to have the failure in one of the span of the bridge. And as you can see in this figure, also you can notice that once we have reproduced, I have reproduced the full progressive collapse of the bridge, there was also a compatible debris distribution between the numerical one, that is the gray one, with the one that has been observed inside. I'm concluding. Here we're at the conclusion. So I want just to say that the numerical method that has been adopted to simulate the structural response of these bridges until the collapse have shown that as-built structural details, as well as changes in the loading and material during their life, can have a relevant impact on the structural response. The applied element method actually has the capability to deal with both standard and non-standard loading scenario, and thus it can be used to estimate the robustness of existing complex structural system from the very initial elastic response until to the debris configuration. This kind of things may represent also a valuable guide for the inspection and monitoring, and also to guide the intervention of retrofit for risk mitigation of existing bridges. For what concerns the two case studies, and I'm concluding, I want to say that the innovative idea by Morandi of introducing only 4 main post-compressed stays seeming ingenious and effective, with no doubt, but combined with the construction errors and the consequent, I would say, non-visible material deterioration through its life, rendered this kind of structure more vulnerable to potential exceptional loads. So I want to say that generally post-compressed structures built in the past or with the technological limitations may hide construction defects, like ineffective injection, as mentioned before by Professor Siviero, that can contribute to the reduction of safety. For what concerns the multi-span arch bridge, the rebuilt Capriola bridge using the 3 inches arch configuration, theoretically isostatic, when combined with unforeseen changes in the hinge struts, carry enlargement, and the years-long slow slippage on one side of the bridge, did inevitably render this bridge more susceptible to the type of complete collapse observed. And the general conclusion in this case is that as-built details constraint characteristics are crucial for the proper functionality of structures lacking robustness. I have concluded, and here are just some of the references of the studies of the results that I've presented. I'm so sorry if I took a few minutes more. Thank you for your attention.
Thank you, Nicola, for your interesting presentation. We have some questions from the audience, also for you, Nicola. There is one question about how you trigger the collapse in the applied element model. Is it element removal or maybe material weakening?
Thank you so much for the comments, so that I can say more about that. Initially, the preliminary studies, we induced the failure of the stay. So the answer is element removal. But then later, in the later studies that I have shown later, for instance, the simulation of the collapses induced by the falling of the steel coil, actually that was just a consequence of the demand that was generated in the stay, in the critical section, due to the falling, in that case, of the steel coil on the bridge deck.
There is another question for you regarding how concrete hinges were formed in concrete. In steel bridges, it can be done easily, but for concrete structure, how?
I'm sorry, I didn't understand very well the first part of
It's about concrete hinges, how
Okay.
they were modeled, I think. That is the question from the audience.
Okay, thank you. Okay, essentially, in case of concrete hinges, is different from steel hinges because with the concrete hinges we have a physical dimension of the hinges. So essentially, the concrete hinges are made usually of crossing rebars. Maybe I can share again the screen so that you can actually you see my. Can you see? Yes, you should. For instance, in this case, I don't know if you see the pointer, you have this cross rebars, and in this portion you have a minor portion or a reduction of the concrete section that allows to the concrete hinges to be able to rotate. So it is simply explicitly modeled by taking advantage of the structural details and explicitly modeling the hinge throat dimension.
I think there is another question from Professor Siviero. Erika?
Yes, there is a question for the presentation of Professor Siviero by Caterina Caffari. I'd like to ask Professor Siviero if institutions ever considered to build a new bridge near the collapsed one, leaving the remaining part of the collapsed bridge may support in the construction of the new one, plus give time to do a proper consolidation and allow to do all kind of tests to detect the causes of collapse, as you said, Professor. And in future years would have allowed to do tests and collect inspection data that are fundamental for research in pre-stressed concrete bridges, predictive maintenance, and avoid demolition cost, and so on. At the same time, the new bridge would be used to quickly restore the interrupted traffic, ensuring up-to-date safety standards. It's a long question, but
no, but I unfortunately, it was not taken into consideration. There are a lot of faults in this situation. First of all, they made a kind of tender which was a false tender because they decided immediately to destroy the bridge and make a new bridge, and this new bridge should be designed by Renzo Piano. This is very clear now. Nobody took into consideration really to get the bridge as it is. There was another point. Originally, the tender provided that the new bridge should be replaced the old one. So the demolition of the bridge was justified to put the new bridge exactly in the position of the UR. Probably they could use also the foundation because the foundation are very strong. The best solution was to build in steel the new bridge. The shape of Renzo Piano. By the way, the shape, the cross section of 100 meter span has been used also for the 50 meter span, which is a nonsense from a point of view of the structural engineer. But anyway, he's the master, he's Renzo Piano, as Aristotle, ipse dixit. This is my point of view. Of course, we lost a lot of information. We had the possibility to see also the effect of a construction that it was really one of the reasons, maybe, or probably the most important reason of the collapse. And we have lost. And I make myself as everybody all over the world was astonished to demolish a bridge like this. Another point: the total cost of this was around 600 million euros. Getting the new part the collapsed part organized in a new way and refurbishing completely to get the safety situation for the seismic cost less than 200 millions, avoiding all the people that had to move because there are more than 200 apartments that have been left. I mean, there are a lot of reasons why this decision is totally unbelievable, but politically decided. All the politicians were together. I mean, there is no need left, right, center, all. They decided like this because they consider the bridge was a murder. This is the point. The social and The communication system, as usual. If you ask any citizen of Genoa, they really consider that the bridge was to be demolished because of technical reason, which is not true. Of course, there are a lot of mistakes, not designing, but execution and lack of maintenance. This is very clear. So what I say, I lost 10 years of my life for that.
Thank you, Professor. And there are also another couple of questions. The first one for Nicola, but it's also a congratulation for you and the IABS Best PhD Award. And also regards to Professor Siviero, there is this beautiful thank you for both of you. And the question for Nicola was, which software was used for the analysis with the applied element method? So we answer a couple of questions with this one, because
Yes.
a couple of people.
Okay, the software that has been used, I don't know if we can declare in this session. Just let me know. I don't know for. I mean, for me there is no problem. And the software used was extreme loading for structures for the studies that I presented in this presentation.
And another one, I don't know, Filippo, if you want to read another one.
Yes, thank you. Okay, there is also another question about the applied element method, how long it takes for the analysis results.
Okay, it depends to which scenario we
Yes.
think. But let's say that the complete collapse, it took around 10 hours.
Considering they were huge models computationally,
Yes.
do you think they performed a lot better than finite
Yes,
elements?
for sure. The main advantage of the applied element method formulation is that given that it is based also on implicit numerical solution, it is much more faster with respect to the explicit methods on which are based the traditional discrete element methods and other softwares that are commonly used. So for sure, there is no comparison with respect to traditional discrete element methods and finite element modeling.
Okay, thank you. Also, there is a question about material deterioration in applied element method. Can be incorporated.
Yes, of course, we can incorporate this kind of effects. It's up to the modeler then to say how this let's say degradation has to be modeled or considered into the modeling, because as you probably know, there are different approaches that we as engineers can adopt to consider these effects, but you can. The easiest one is to adjust both. For instance, if we think to the steel corrosion, for instance, the one induced by pitting corrosion, we have to adjust both the material relationships, so steel in this case, for instance, we speak about steel, but also we can also introduce some modification about the residual area that we have into the rebars. From a numerical and mechanical point of view, this implied that we are going to adjust the properties of the springs that are representing the steel reinforcement. Of course, similar considerations can be also done for the concrete. We want to simulate a degradation of the concrete itself.
Thank you, Nicola.
Welcome.
Thank you so much. And I'd like to ask Professor Siviero about a curiosity about starting from this first webinar about great engineers, if you, or both of you, if you could advise us on other great engineers that we could discuss in upcoming webinars, and starting with today's webinar on Morandi, are there any designer, in your opinion, who have direct links to the works of Riccardo Morandi that could be interesting to discuss?
I think Riccardo Morandi is the most famous, but there are other great engineers. Giulio Kral, for instance, who was less known, but he made maybe more bridges than Riccardo Morandi. He was also professor of dynamics of structures. He was a director of a Ferrocemento company. Another one is Carlo Cestelli Guidi, who is most known for the book on pre-stressed concrete, on foundation, and so on. Silvano Zorzi. My mentor, Giorgio Macchi, who died just a couple of years ago. Fabrizio De Miranda. Fabrizio De Miranda is the most important bridge designer in steel, and his son Mario is a very friend of mine. By the way, next year it will be 100 years of his birth, and I am trying to prepare a monography with my magazine Galileo. I try to understand that engineering is great, not only architects, and this is another point. I can tell you at least 3-4 Italian designer more, but in some of them they made just 1 or 2 bridges. Santarella, for instance, Genio Miozzi. Then now I can think about. But anyway, I made also the history of the Italian engineers, and I made a lot of master theses also for the other engineers all over the world, even living, because there are not the people that died. For instance, Pino Mancini is a very important one, Fabio Brancaleone. I mean, we should, as IAPSE, show that engineering is more than what we know. Because in Italy, we don't have the aptitude, the possibility to show what we do. In general, I was, until a few years ago, I was moving all around the world, practicing all the most important congresses on bridges. Really, very, very few Italians are present. There is another reason. In IAPSE, all over the world, the most important participants are contractors or designers, not only academicians. In Italy, the people that move around the world is just academicians. For a lot of reasons, maybe that we have another line. I see that they are proud to present a lot of things that they have done through them and other contractors. Anyway, I'll give you some connection, because I made something like 80 master theses on great personalities of engineers, also from 800, of course, not only 900, but 900 is the concrete century, therefore, which is the most important. And only after the Second World War, we started building steel, and now steel is more important for the velocity mainly.
Yeah, thank you, Professor. As you took a great point about the fact that also structural engineer is a heritage, a legacy that must be preserved, or even just a legacy to raise awareness in order to be better recognized. And we think that these kind of webinars, as well as all the work that every one of you is doing, is pushing in this direction. And we would like to thank you.
May I precise 2 things? First, Martinez, who was also, Martinez y Cabrera was also a very great bridge designer, invited me his seminars 20 years ago, and I talk about engineers and architects. He was very, very interested in that part. The second is I made a lot of seminars in Venice, mainly, named Bridge Italy, showing that also young engineers are good engineers, and there are a lot of 10 or 15 good young engineers, with respect to my age, of course, not to your age, but I think that the IAPSE Italy should push this line, as they do all over the world. If I talk, for instance, Millau Bridge was presented 20 years before the starting. Michel Villageot was invited by me in Venice, showing the different approach, and just to reach the goal, going through the history of the design. This is very important. And also the example, how was the problem of execution, which normally is ignored because it seems the problem of the contractor. No, it's again the problem of the brain of the engineers. So this invitation for me is a kind of very good gratification. And I think it is a very important point. I'll do my best to follow you as much as you like.
Thank you very much, Professor. And I leave the screen to Fabrizio Palmisano for the final conclusion of this webinar as a Vice President of the IAPSE Italy chapter.
Thanks, Erika. And just I would like to add from the audience some suggestions about great engineers. We have to remind Pierluigi Nervi, Sergio Musmeci, but I would like also to emphasize that this kind of series of webinars that we have started today, and I would say successfully started today, will be devoted also, I hope, to not only Italian structural engineers, but also for all over the world. For example, the one mentioned by the Professor Siveri. And with this, I would like to thanks again the speakers, Professor Sivero and Dr. Scatareggia, for a very interesting and valuable presentation. I would like to thank them also on behalf of the chair of the Italian group of IAPSE, Professor Limongelli, who was not able to join today for another institutional meeting. I would like also to thank the two moderators for their great job in this webinar. Thanks, Erika, and thanks, Filippo. And with this, I think we have to conclude, and I hope to meet you all again in the future webinars organized by IAPSE and by the Italian group of IAPSE. Thanks a lot, and bye-bye.
Thank you.
Bye.
Thank you.